All right, let's be honest. In our last video, we gave our agent a superpower, dynamic programming. It was like having a perfect satellite map of a city, a map with a godlike view. This perfect map is the model of the world. Look at this diagram. With a model, the agent knows the exact probability of everything that could possibly happen. But here's the catch. What happens when you don't have a map? What if you have no model? You don't know the rules. You have to learn by just walking around. Check this out. Now the probabilities are all question marks. We have no idea what's going to happen. This is the giant leap we're taking right now. The jump from being model-based, like with dynamic programming, to being model-free. With a model, you have that perfect map. You learn by calculating. But when you're model-free, you have no map. You learn from experience. So today, we are throwing away the map. We're getting rid of the rule book. We're going to learn from raw, direct experience. This is Monte Carlo learning. By the end of this video, you will understand how an agent learns the best strategy to win, using nothing but its own trial and error experience.
So, how do you learn from raw experience? Well, our agent needs a world to get lost in. A challenge to overcome. Let's build one. We'll call it the slippery race. Imagine a tiny robot on this simple, one-dimensional track. You can see it here on the screen. There's a starting point, S, a few squares in the middle, and a goal, G. The rules are super simple. First, the robot can either move left or move right. Second, every single move costs a little bit of battery, so that's a -1 reward. And finally, reaching the goal gives a big +10 reward. Easy, right? Just keep moving right. What could go wrong? But there's a catch. There's a hidden rule. Look at the diagram again. Square C is slippery. If our robot is on square C and tries to move right to the goal, there's only a 50% chance it actually works. The other 50% of the time, it slips and gets sent all the way backwards to square B. And here's the most important part. Our robot does not know this rule. It has no idea about the 50-50 probability. All it knows is that sometimes when it's on square C, something weird happens. The map is gone. The rulebook is a lie. This single hidden rule, this is the entire reason we need a new way of thinking. This is why we need Monte Carlo. So let's put ourselves in the robot's shoes. It's on square C. What should it do? Option 1 is to move right. It's the direct path, but it's risky. It could win instantly, or it could fail miserably and get sent backwards. Option 2 is to move left. Now, this sounds crazy. Why would you move away from the goal? But it's safe. It's predictable. How would our old model-based agent solve this? Remember the dynamic programming agent from last time? He'd say something like, I need the exact transition probabilities. What's the slip chance? 10%, 50%, 90%? He'd look at his formula here, the P of S prime R given SA, and realize it's incomplete. Without that number, I am completely stuck. He's paralyzed by the unknown. But now, meet our new agent, the Monte Carlo agent. It thinks completely differently. The Monte Carlo agent says, I don't know the slip probability, and honestly, I don't care. What I have is a notebook. Let me check my notes for square C. Okay, the last 100 times I tried to move right, my average final score for the whole race was +2. And the last 100 times I moved left, my average final score was -5. Well, +2 is a lot better than -5. It's an easy choice. I'll take my chances and move right. This is the Monte Carlo mindset. It doesn't need to understand the physics of the slippery tile. It learns from a notebook filled with raw, direct experience. It just looks at what worked best on average in the past and does that. This sounds amazing, right? So practical. But it raises a huge question. The Monte Carlo agent is relying on its notebook. It's evaluating its strategy based on past results. But what if its strategy is just dumb? How can we know if our notebook is any good? That's what we need to figure out next. How do we evaluate our policy?
So one agent is paralyzed by the unknown. The other just pulls out a notebook. This isn't just a cute story. This is the fundamental, game-changing difference between model-based and model-free learning. Let's go back to that critical moment, the choice at square C. As the slide shows, the agent must choose right into danger or left into safety. First, let's remember the model-based thinker, the dynamic programming agent. It says, I need that probability function for the Bellman equation. What's the exact probability of slipping? Without it, I'm stuck. It's completely paralyzed. Book smart, zero street smarts. Now let's look at the experience-based thinker, the Monte Carlo agent. It says, probability? Who cares? I've got something better. Data. I've run this race thousands of times and I kept the notebook. Let me check. Okay, here's the page for when at square C. Last 100 times I chose to move right, my average score was +2. And the last 100 times I chose move left, my average score was -5. The choice is suddenly dumb simple. Well, +2 is a hell of a lot better than -5. I'll take my chances and move right. This is the entire Monte Carlo mindset in a nutshell. It doesn't need to know the physics of the slippery tile. It just observes the final outcomes. It replaces complex probability calculations with a simple, powerful tool: the average of its past experiences. This is incredible, but it immediately leads to a new problem. How does the agent fill this notebook in the first place? To get these averages, it needs a strategy to follow. But what if its strategy is just completely random? So, before we can improve our policy, we first need a way to measure how good or how dumb our current strategy is.
So how do we do that? How do we fill the notebook? How do we measure a policy if we don't have the map? Let's look at the starting point. Our robot starts with a completely dumb strategy, its first policy. As you can see on the slide, it's pretty simple. At any square, there's a 50-50 chance I'll move left or right. It's totally random. Now, let's be honest, this is a terrible policy. But before we can make it smarter, we have to know exactly how terrible it is. This is what we call the prediction problem. Our mission is something called policy evaluation. We need to find the value for every single state under our current dumb policy. We write the value of a status as V of S, which you can see on screen. Now, if you remember from our work with dynamic programming, we used the complex Bellman equation to solve this. But that required the map. It needed to know all the transition probabilities. We don't have that anymore. With Monte Carlo, the approach is, well, it's ridiculously simple. Are you ready? The value of a state is just the average of the final scores you get starting from that state. That's it. That is the entire idea. So how would we find the value of square B, or V of B? Well, let's look at the steps. First, you'd run a ton of races that either start from or just pass through square B. Second, for each of those races, you'd note the final reward you got from the moment you first hit square B. You write all those final scores down in the notebook. And finally, you just average them. It sounds almost too simple to work, doesn't it? So let's make this crystal clear. Let's actually calculate the value for one of our states, square B, race by painful race. Okay, so our mission is to calculate the value of being in state B. We'll call this value V of B. As you can see, the notebook page for V of B is completely blank right now. We have absolutely zero data. So let's get some. Here's the setup. You might remember it, the slippery race. Our policy is simple. There's a 50-50 chance of moving left or right from any square. The rewards are -1 for every move we make, but we get a big +10 for reaching the goal. And don't forget the hidden rule. Moving right from state C has a 50% chance of slipping you all the way back to B. Let's run our first episode. Okay, look at this path on the diagram. We start at S, go to A, then we hit B. From B, we go to C, and whoops, we slip back to B. Then to A, back to B, over to C, and finally, we reach the goal. A long winding road for sure. Now here's the key question. What was the score from the first time we visited B? Let's trace that sub-journey. From that first visit to B, it took us 6 more moves to reach the goal. So that's 6 moves times -1 plus the 10 points for finishing, which gives us a total score or a return of +4. Great. Let's open our notebook for state B. We'll write down that return, 4. And with only one data point, our current best estimate for the value of B is just 4.0. Let's go again. Episode 2. This time, we get a much luckier break. We go from S to A to B, then from B we go to C and straight to the goal, no slipping. So what's the return from our first visit to B this time? Well, it only took 2 moves to get to the goal. So that's 2 moves times -1 plus 10 for a return of +8.
Back to the notebook. We add the 8 to our list of returns. Now we have a 4 and an 8. Our new estimate is the average of those two, which is 6.0. See how this works? Let's do one more. Episode 3. And we get another slip. Look at the path. We go from B to C, slip back to B, then go C to G. So from that first visit to B, how many moves did it take? 4. 4 moves at -1 each, plus the 10 for the goal. Give us a return of +6. Let's update the notebook one last time. Our list of returns is now 4, 8, and 6. The new average is, well, it's still 6.0. So, after just 3 races, our estimate for the value of being in state B is 6.0. Now, here's where it gets powerful. Imagine we don't stop. Imagine we run for 100 episodes, then 1,000, then 100,000. Each time, we add another return to our list. That list gets absolutely huge. But thanks to something called the law of large numbers, the average gets closer and closer to the true value. It converges. We didn't need a map. We didn't need to know the rules. All we needed was a notebook and patience. This simple manual process of running episodes and averaging the results, this is the absolute heart of the Monte Carlo method. Now, let's formalize this into a proper algorithm we can actually code.
Okay, check out the algorithm on screen now. Now, I know what you're thinking. That looks like complex code, but I promise you, this is exactly what we just did with our notebook. It really just boils down to 3 simple steps. First, you play. You run a full episode, following whatever policy you have. Second, you work backwards. You start from the end of the episode and calculate the final score, or the return, from each point in time. And third, you average. You look at each state you visited, and if it was the first time you landed there in that episode, you update its running average value. That's it. Play, work backwards, average. Simple. Now, a quick note. You might have noticed I kept saying the first time you visited a state. This leads to a little distinction in Monte Carlo methods. First visit versus every visit. Look at this example path. You can see the robot hit state B multiple times. With first visit MC, which is what we've been doing, we'd only count the return from that very first time we landed on B. That gives us 1 data point from this whole episode. But in every visit MC, you'd remove that if statement in the algorithm. You'd count the return from all 3 visits to B, giving you 3 data points. So which one is better? Honestly, it doesn't really matter. First visit is the standard you'll see in most textbooks, and it's a little easier to prove mathematically. Every visit uses more data, so it can sometimes learn faster. The key thing is both of them converge to the correct answer. So for the rest of this course, we'll just stick with first visit. Okay, we've done it. We have a robust, formal method to calculate the true value of every single state. And we did it all without a map. This is a huge achievement. But it leads to a devastatingly simple question. So what? I mean, knowing that the value of being at state B is 6.0 is nice, but how does that actually help the robot decide whether to move left or right when it's standing there? It tells us how good it is to be at a state, but not what to do there. And that reveals a critical hidden flaw in our whole approach so far.
So, let's be real. We just did all that work. We ran thousands of simulated races. We filled up pages of our digital notebook. We even built a beautiful algorithm to calculate the value of every single state. And now we have all this data. We know that under our dumb random policy,
The value being in state B is about 6.0. The value of state C might be 7.5. And then the robot asks a devastatingly simple question. So what? I'm in state B. I know its value is 6.0. That's nice. But it doesn't tell me what to do. Should I move left or should I move right? Now, the obvious sounding answer is a trap. It's what I call the model-free trap. The robot's flawed logic goes something like this. Check out the diagram. Okay, from state B, I can see that the value of A is 4.0 and the value of C is 7.5. Clearly, I should move right to the more valuable state. This logic seems flawless. It's also completely, fundamentally wrong. Why? It's because of one single word. Probably. Think back to dynamic programming. We had the map, we had this formula, we knew the exact odds of where we'd land if we took an action. But with Monte Carlo, we're model-free. We threw the map away. And you can't decide based on a destination's value if you don't know which road even leads there. It's like knowing a state's value is like knowing the answer to a test question, but you don't have the question. Let me make this crystal clear with an analogy. Imagine you're planning a vacation. Your friend tells you Paris is a 9 out of 10 city, and Rome is a 7 out of 10 city. Okay, great. You now have state values. The value of Paris is 9, the value of Rome is 7. Now what? You can't just pick Paris because it has a higher value. To make a real decision, you need to know about the actions. Look at the details here. The flight to Paris is 20 hours with 3 layovers and costs $2,000. But the flight to Rome, it's a 2-hour direct flight for $300. Knowing the value of the destination isn't enough. You need to know the value of the journey. So we spent all this time learning this powerful new tool, Monte Carlo evaluation, only to discover that it's useless on its own. So, how do we fix this? What if instead of learning the value of the destination, we could learn the value of the journey? What if we can learn the difference between how good it is to simply be in Paris versus how good it is to take the flight to Paris? So, how do we fix this? How do we learn the value of the entire journey, not just the value of the destination? We do it by changing the question we ask. Instead of asking, how good is it to be in state sites? We're going to ask a much more powerful question. How good is it to take action S from state sites? This single change in perspective is the solution to our entire problem. This new value isn't called a state value, it's called an action value. Or by its much cooler, more famous name, the Q value. Let's make this crystal clear. Look at the screen. On one hand, you've got V of S, the state value. That's the average score starting from this state. It's the value of the destination. On the other hand, we have Q of S, A, the Q value. This is the average score from taking this action from this state. It's the value of the entire journey. This Q value is what our agent was missing. It's like getting the cost of the flight, the hassle of the layovers, and the quality of the final destination all bundled into one simple, beautiful number. And here's the best part. To calculate these powerful mu-q values, we just need to make one tiny change to the method we already learned. Check this out. This was our old algorithm for state values. We initialized V of S, kept a list of returns for each state, and averaged them. Simple enough. Now, look at the new upgraded algorithm for Q values. See the difference? It's tiny. Instead of V of S, we have Q of Site. Instead of a list for each state, we have a list for each state action pair. That's it. That's the whole change. So instead of keeping a list for each state S, we now keep a list for each state action pair, What's-ite. Think of it like our robot's notebook. It no longer has a page just for state B, it now has 2 pages. One labeled state B move right, and another labeled state B move left. Let's see this in action. Remember our old episode? The robot moved right, slipped, moved left, and eventually got to the goal. Just like before, the first step is to work backwards and find the return from each point in the journey. So the return from the last time it was in state B was +9. The return from the last A was +8. The return from that middle visit to B was +7, and so on. We've done this part before.
But now we update our Q-value notebook using that first visit rule. Let's walk through it. First, way back at the start, in state S, the robot took the action right. The return from that point was +3. So we add a +3 to the list for the pair S right. Next, in state A, it took right, the return was +4. So we add +4 to the list for A right. Then, in state B, it took right. The return was +5. Okay, so we add +5 to the list for B right. In C, it took right, return was +6. So we add +6 to the list for C right. And here's the interesting part. The next new pair was in state B, where the robot took the action left. The return from there was +7. So we add +7 to the brand new list for B left. And because we're using the first visit method, we just ignore the later times it visited pairs we've already recorded in this episode. Now for the payoff. When our robot is standing in state B, it can now look at its notebook and make a real decision. It looks at the page for QB right. There's only one data point so far, +5. So the average is 5.0. Then it looks at the page for QB left. It also has one data point, +7. The average is 7.0. The choice is suddenly, beautifully, dumb simple. 7.0 is greater than 5.0. Based on just this one experience, moving left looks like the better move. There's no model. There are no probabilities. It's just a direct comparison of the outcomes it has actually experienced. This is the breakthrough. With Q values, our agent finally has a clear, direct way to compare its choices and improve its policy. But this simple solution immediately creates a new, much more subtle problem. Think about it. If moving left from B gave a better score so far, how will the agent ever get more data for moving right from B? What if that first race was just a fluke, a lucky run? To get the best score, we want to exploit the actions we already think are best. But to find the best actions, we need to explore all the other options, even the ones that look bad right now. This is the classic fundamental dilemma of all reinforcement learning. Exploration versus exploitation. And finding the right balance between these two is the final key to unlocking true learning. We just handed our agent the keys to the kingdom, Q values. It seems like we've solved it. The path to the optimal policy looks simple, right? First, you calculate the Q values. Second, you always choose the action with the highest Q value. Simple, perfect. But this perfect, logical sounding plan is a trap. A subtle, dangerous trap that can lock our agent into being mediocre forever. Think about it. After one race, our robot looks at its notes. It thinks, okay, the Q value for being in state B and moving left is 7.0, but the Q value for B and moving right is only 5.0. So it updates its policy. When at B, always move left. If it always follows that rule, it will never, ever choose to move right from B again. Its knowledge is frozen in time, based on one single unlucky experience. What if moving right is actually the masterstroke, the key to winning? The robot will never find out. This leads to one of the most famous problems in all of AI, a problem you face every single day, the dilemma of exploration versus exploitation. Let me ask you a question. If you always do what you think is best, how will you ever discover something better?
Think about your favorite pizza place. It's a solid 8 out of 10. Going there is reliable. That's exploitation. You're guaranteed a good reward. But what about trying that new place down the street? It could be a 10 out of 10, or it could be a 2 out of 10. That's exploration. It's a risk for the chance of something better. And here's the trade-off. If you only exploit, you're stuck with 8 out of 10 pizza forever. But if you only explore, you're probably going to suffer through a lot of terrible meals. This is the exact choice our robot faces at every single step. Exploitation is picking the action with the highest known Q value. It's the safe bet. Exploration is trying any other action. It's a gamble for new knowledge. So here's the thing to remember. To find the truly optimal policy, you can't just be greedy. You must explore. The entire challenge of Monte Carlo control comes down to this balance. How do you build an agent that knows how to find the 10 out of 10 restaurant, but still gets to enjoy it once it's found? The first solution is to bake that curiosity right into the policy itself. We're going to make our agent just a little bit unpredictable.
So how do we build an agent that's greedy enough to win,
but curious enough to learn?
The solution is a shift in thinking. Stop thinking of exploration and exploitation as separate modes. Instead, we bake curiosity right into the agent's personality. This philosophy is called on-policy learning. Here's the analogy. On-policy learning is like learning to cook by tasting your own food. You have a recipe, that's your policy. You add a pinch of random spice, that's exploration. You taste the final dish, that's the return. And based on that taste, you update your recipe. The key is, the recipe you're using is the exact same recipe you're trying to improve. You learn and act with one single policy. Now, the most common way to do this is with a beautifully simple strategy called Epsilon-Greedy. We pick a small number for our curiosity level, epsilon, let's say 0.1. This means that 90% of the time, the agent exploits. It chooses the action it believes is the absolute best. But 10% of the time, the agent explores. It ignores its Q values completely and chooses an action at random. That's it. It's a beautifully dumb, simple rule. Most of the time, be greedy, but sometimes be curious. Now, in the textbooks, you'll see a formula that looks a bit scary. Check this out. Okay, let's be honest. That looks like alien math, but it's just a fancy way of writing our simple rule. Let's make it concrete. Imagine our agent is in state P. It has two options, left or right. Our curiosity, epsilon, is 0.1, and our Q values tell us that moving right is the best action. Let's plug these into that formula.
Okay, look at the first calculation here. What's the chance of picking right, the best action? Well, the formula is just a formal way of saying we take our 90% chance to be greedy and add the small slice of the random exploration that happens to land on the best option. When you do the math, it comes out to 0.95, a 95% chance. Now, what about the chance of picking left, the other action? The formula for that is much simpler. It's just the exploration probability split among all the non-best actions. In this case, that's 0.1 divided by 2, which gives us 0.05, a 5% chance. See, it's exactly what we said. The agent exploits its best option 95% of the time, but reserves a 5% chance to explore. With this simple rule, the agent can never get stuck. It's guaranteed to eventually discover those hidden gems. So, the entire on-policy learning loop looks like this. First, you follow your Epsilon-Greedy policy for a whole race from start to finish. Second, you calculate the returns for every state and action pair you visited. Third, you update your Q values by averaging in these new returns. Then, you improve the policy, which just means your new Q values now define a new Epsilon-Greedy policy. And finally, you repeat. This is our first complete working control algorithm. But that raises a subtle and important question. With this method, we're learning the best way to act if you're always forced to be a little bit random. We're not learning the single, perfect, 100% optimal path. We're learning the best pack for an explorer. What if we want both? What if we want to explore like a toddler, but learn like a champion? To do that, we need to separate the act of exploration from the act of learning. We need two policies, not one. This is a different philosophy called off-policy learning.
So that raises a really subtle but important question. How do you explore like a curious toddler, but use that experience to learn the perfect strategy of a world champion? How can you have the best of both worlds? The answer is, you live a double life. You completely separate the act of exploration from the act of learning. This is the second major philosophy of learning we're going to explore. It's called off-policy learning. And the idea is to use two different policies. First, we have the behavior policy. This is the one the agent actually uses to move around. Think of it as our curious toddler. Its job is just to try things out. Then we have the target policy. This is the one we want to learn about. This is our world champion, the perfect optimal strategy. So the core idea is simple. You follow the behavior policy, but you learn the target policy. The single best analogy for this is a student driver learning to be a Formula One champion. The student's cautious, clumsy driving, that's the behavior policy. It's full of exploration and mistakes. The champion's perfect, aggressive racing line, well, that's the target policy. It's what we're aiming for. So picture this. The student is driving slowly, cautiously, exploring the track. But then they go home and watch recordings of the champion taking that same corner at 200 miles per hour. They're learning from an expert even though their own actions are still clumsy. This changes the goal completely. Let's look at the difference. With on-policy learning, the goal was to find the best policy that still has to explore. You're finding the best, cautiously adventurous path. But with off-policy learning, the goal is much bigger. We want to learn the Q values for the true optimal policy. No compromises are needed. We can act like a beginner, but learn like a pro. But this raises a huge and seemingly impossible question. How can you learn about the champion's aggressive strategy while you're following your own cautious one? The data you're collecting doesn't match the policy you're trying to learn about. It's apples and oranges. The answer is a clever mathematical trick, a way to translate the student's experience to be relevant for the champion. This trick is the secret sauce, and it's called importance sampling.
So we have a problem. A big one. You see, our student driver is the one out there generating all the data. But we're trying to learn the strategy of a world champion. The data is biased. The experiences we're collecting don't match the policy we actually care about. It's apples and oranges. So how do we fix it? How do we bridge this gap? We need to mathematically correct for this bias. We need a bridge, a way to connect the experiences of the explorer to the knowledge of the pro. This correction, this secret sauce that makes off-policy learning work, is called importance sampling. Think of it like this. Every time our student driver takes an action, we just ask one question. How likely was the champion to do the exact same thing? It's pretty simple, right? If the champion was likely to do it, then that experience is important. We should pay close attention. But if the champion would never do that, well, then that experience is pretty much useless for learning the champion's strategy. So, importance sampling gives us a weight for every single experience. And that weight just tells us how relevant it is. And when we bake this idea into our full Monte Carlo algorithm, well, it looks like this. Okay, stop. Don't panic. I know that looks like a monster. It's got a W, it's got fractions, and a scary-looking update rule. But I promise you, this is the key to everything. This is how you can watch a beginner play, but learn to be a grandmaster. So next, we're going to break down this algorithm. We'll figure out exactly what that W means and how this whole thing actually works.
All right, let's slay the monster. So, just to recap where we are, we have the student driver, who is out there generating all of our data, and then we have the champion, the pro policy we're actually trying to learn about. The bridge that connects them, the secret sauce,
is importance sampling. Now, we're going to walk through what happens when we use it, step by step. No more scary formulas for a minute, I promise. We're just going back to our simple race, our 2 policies, and our 1 mission. Here's the setup. We have our target policy, the champion, who is perfect and always goes right. And we have our behavior policy, the student, who is just exploring, randomly, 50-50. Our mission is to learn the true value of going right from state A, if you act like a pro for the rest of the race. So let's see what happens. In our first episode, the student gets a perfect straight shot to the goal. You can see the path right here. We do the math. We find the return, which is +7. Then we calculate that importance sampling ratio, which comes out to 8. And when we multiply them, our first corrected return is +56. Okay, not bad. Now, for episode 2. This time, our student takes a little detour, slips, and has to repeat a step. It's a longer path. Again, we do the math. The return for this longer path is +5. But look at the ratio. Because it was a longer sequence of right moves, which is unlikely for the student, but guaranteed for the champion, the ratio blows up to 32. And our corrected return? It's a massive +160. Whoa, hang on. What about an episode where the student goes left from A? Well, since the champion would never do that, the whole episode is irrelevant for this specific question. We just throw it in the trash. So let's take stock. After just 2 useful episodes, our notebook for this state action pair has 2 corrected data points. Look at those numbers. +56 and +160. The variance is huge. This is a massive, dangerous new problem. A single rare event with a crazy high importance sampling ratio, well, it could completely derail our learning. It could poison the average. You see what's happened? We successfully corrected for the bias of using the wrong policy's data. But in doing so, we've introduced these wild, unstable swings.
We've traded one problem for another. I know what you're thinking. If you just take a simple average of these numbers, your estimate is going to be a disaster waiting to happen, and you are 100% right. This simple averaging method, it works in theory, but in practice, it's garbage. It's just too unstable. We need a better way. We need to use a weighted average. This one tiny trick is what turns this cool idea into a practical working algorithm. Here's how we do it. For each state action pair, we're going to keep track of 2 numbers. First, Q, our current best estimate, and second, a new number, C, which is the cumulative sum of all the importance ratios we've ever seen for this pair. Think of C as the total weight of evidence. Then, we use this new update rule you see here. I know it looks a little scary, but it's just a weighted average in disguise. The key part is that we divide the new weight by the total weight of all the evidence we've seen so far. This forces our estimate to stabilize over time. Let's prove it. Let's rerun our exact same example. We start with Q equals 0 and C equals 0. Okay, episode 1, the return was +7 and the ratio was 8. First, we update our cumulative weight, C. It was 0, now it's 8. Then we plug everything into our new Q update formula. Check it out. After our first episode, our estimate for Q is exactly 7. So far, so good. Now for the big test, episode 2. This is our high variance sample with a return of +5 and that massive ratio of 32. Let's see if our new rule can handle it. First, update the cumulative weight C. It was 8 and we add the new ratio of 32, so our total weight of evidence is now 40. Next, we update Q. We plug in our old Q of 7, our ratio of 32, our new C of 40, and our new return of 5. And what do we get? Our new estimate is 5.4. Look at that. Just look at it. That high variance sample did have a big impact. It pulled our estimate down from 7 towards 5, as it should. But it didn't destroy our old knowledge. It didn't completely overwhelm the estimate. It acted as a sensible, self-correcting learning rate.
This is the magic. This is what makes off-policy Monte Carlo work in the real world. We tamed the variance. We slayed the monster. The simple average gave us a crazy estimate of 108, completely thrown off by one wild sample. But with weighted importance sampling, our estimate was an incredibly stable 5.4. The high variance sample pulled our estimate, but it didn't overwhelm it. That little tier term acted as a smart, self-adjusting learning rate. As we gather more data, the total weight C grows, and the effect of any single new episode gets smaller and smaller. This allows our estimate to converge smoothly and stably. This is how we tame the monster of variance. This is the final piece of the off-policy puzzle. We can now actually use a student's biased, messy experience to learn the perfect, stable, optimal strategy of a world champion. This is a massive achievement, but Monte Carlo methods, for all their power, have one glaring fundamental weakness. A weakness that makes them painfully slow. And understanding that weakness is the final step on our journey before we leap into the true heart of modern reinforcement learning.
We've done it. We have successfully built a system where an agent can learn from scratch. Just think about what that means. We've built an agent that can learn without a map, just by playing the game. We shifted our entire perspective to focus on Q values, and we tackled the fundamental exploration dilemma with two amazing strategies. Look here, we have the on-policy approach using Epsilon-Greedy and the off-policy approach with importance sampling. Monte Carlo learning is a massive leap forward. But it has one significant, glaring, and frankly painful flaw. It is incredibly slow. The reason is that Monte Carlo methods only update their knowledge at the very end of an episode. The agent has to play an entire game from start to finish, get the final score, and only then can it look back and learn anything. Let me make this painfully clear with an analogy. Imagine you're playing a long, intense game of chess. On turn 5, you make a brilliant move, a stunning queen sacrifice that just cracks the opponent's defense wide open. It's a work of art. The game continues for another 35 turns. But then on turn 40, you get tired. You miscalculate, you make a stupid, simple blunder, and you lose. The game is over. The final score is -1. Now, the Monte Carlo agent analyzes this episode. It sees the final outcome was a loss. And what does it do? It assigns that negative outcome to every single state action pair in the entire game's history. It blames the blunder on turn 40. Sure, that makes sense. But it also blames the brilliant queen sacrifice on turn 5. It has no way to know which move was good and which was bad. It just sees the final score and paints the entire history with the same brush. This wait until the end approach causes two huge problems. Look at this slide. First, high variance. One lucky or unlucky action at the end completely misleads the agent about all the great moves that came before. Second, it's just slow learning. If you have an episode with 1,000 steps, you only get one update. It's such a waste of experience. This limitation begs a crucial question. A question that will lead us to the true heart of modern reinforcement learning. Can we get the best of both worlds? Can we learn step by step, learning from our mistakes immediately? And can we do all of that, but do it without a model, learning directly from pure experience? The answer is a resounding yes.